So we have been studying eigenvalues and eigenvectors of operator. So last time I just had an thing that we solved the eigenvalue problem. उसको हम कैसे in terms of differential equation solve करते हैं. In today's class, what we are going to study is commuting observables and simultaneous measurements. So, what do you mean by commuting observables? So you might be aware of, for example, an eigenstate is being operated upon by an operator. Okay, that will give a particular eigenvalue, a unique eigenvalue. So that will correspond to our measurement. ठीक है. अब ये है कि when we say of commuting observables, it means two or more measurements which are basically done by operators acting on eigenstates which will give particular eigenvalues. You can simultaneously do it. So there is not in principle any problem in that. But later we'll see that once we formulate or formalize in the next class uncertainty principle, that it's not, this is the way quantum mechanics fundamentally starts. So in principle, you should have no problems for commuting observables. Two or more observables, you can simultaneously measure them. So in that language, commuting means if the operator in this language, if they are commuting observables, PQ is 0. So PQ minus QP. So you can simultaneously measure the values of eigenstates which are being operated upon by operators which will give some unique eigenvalue. You got my point? So this is the thing. And you can simultaneously measure. So this is this much is fine. Now हमारे पास जो था since would have been used throughout, we are using Hermitian operators. So the use of Hermitian operators was special because in principle जो wave function है उसको हमने psi के साथ relate किया था. Some psi is a complex quantity. But Hermitian operators को use इसका जो solution है ना उसकी values real आते हैं. That makes it the properties of Hermitian operators जो हैं the solutions come out to be real.
That's why we even use it to get the continuity equation. If the operator was not Hermitian at that time, we won't be able to get that version of continuity equation.
That's beside we're this time focusing on why the use of Hermitian operators in getting, because we are interested in the eigenstates, eigenvalue. अब यहाँ मसला आ रहा है कि there are two or more eigenstates which will correspond to two or more eigenstates which will correspond to some unique eigenvalue. ठीक है? So if two or more eigenstates or they will have correspond to one eigenvalue or rather repeated eigenvalues, तो अगर हमारे पास ऑर्थोनॉर्मल स्टेट्स हैं लेफ्ट हैंड साइड में, so orthogonal states का ये है, so they may correspond to unique, so that corresponds to linearly independent equation. So you can have it, but for orthonormal basis correspond to unique or a single eigenvalue. What does it mean? ठीक है? That's the point. So I'll just write it. So what we mean by that? So for orthonormal states, क्योंकि हमने कहा था फॉर एग्जांपल व्हेन दिस ब्रॉडकास्ट नोटेशन ए एक्टिंग ऑन दिस साइड इट विल गिव अस a prime it will give us what I should say we start हमने ऐसे किया था so I'll not write psi it's a prime is a prime so this acting on this is state psi so it will give us this it will have some value a prime right है ना a prime अब यही है so if it's two or more orthonormal states will correspond to some unique eigenvalue ठीक है एक ही value जिसको हम not orthogonal but orthonormal states ठीक है so इसका मतलब क्या है इसका मतलब है कि जो हमारे पास जो जनरल डेफिनेशन ऑफ मैट्रिसेस था यूनिटरी ट्रांसफॉर्म एक है कि ऑपरेटर्स कैन समटाइम्स बी रिप्रेजेंटेड एज मैट्रिसेस ठीक है फॉर एग्जाम्पल साई ऑफ आई इज इक्वल टू ए आई जे साई ऑफ जी ठीक है सो यू कैन गो फ्रॉम स्टेट साई टू स्टेट साई बट इट इज बीइंग mediated by this matrices है ना ये मल्टीप्लिकेशन जे जे विल कंट्रैक्ट इट विल साई आई
You can think of it as a linear transform.
हाँ लीनियर ट्रांसफॉर्म अब मसला ये है कि दिस ऑपरेटर डेफिनेशन मे और मे नॉट ऑलवेज कोइंसाइड will correspond to operated upon by operators and they will give different eigenvalues in this Hilbert space. So the choice of basis, how you choose your basis set will make will be unique to the thing we are studying. तो जो हमारे पास ऑर्थोनॉर्मल स्टेट्स यहाँ पर आ रही हैं which will correspond to some unique eigenvalue so you have to take into consideration हमारे पास basis states क्या है ठीक है और यहाँ पर there is another question is that जो हमारे पास unique basis states है so is there is only one unique way of two repeated eigenstates will have a unique eigenvalue. So is there any other way that two or more eigenstates will choose the same eigenvalue? Apart from the considerations of the way we have defined orthonormal states. So here comes a system may be symmetric or not. A system may be
Symmetrical.
no or not. So there can be other variables, not necessarily coming from this thing, which will let us know that systems they will choose some particular value. So there can be other considerations by which we can arrive about the at the same thing. So this is the point. So that will correspond to the symmetry of the system. हमारे पास क्या है symmetry of the system या क्या है? For example, or you can say additional observables that share common or simultaneous eigenvectors with operator A but are sufficiently different from A so that their eigenvalues can serve as distinguishing indices for eigenvectors. belonging to repeated eigenvalues, belonging to repeated eigenvalues. ठीक है? तो what I want to say is first let me summarize. हमारे पास so हमारे पास eigen states का you get a given a unique eigenvalue. ठीक है? Operator acting upon state get, ठीक है, it will give a unique eigenvalue. ठीक है? अब ये eigen states जो हमारे पास हैं they may be orthogonal or they may be orthonormal. Orthogonal states can also come to a unique eigenvalue. ठीक है, वो तो पता है different orthogonal. So if it is an alpha 1 a1 plus alpha 2 a2, the alpha 1 is equal to alpha 2 is equal to 0. But if it's an orthonormal state, they are coming to some unique eigenvalue. ठीक है, so that's the thing, or repeated eigenvalue. So that's the thing. So what does it say? So अब ये है कि so we can, is there any another way by which even if the two eigenstates which are operated upon by operators, they will lead to some unique eigenvalue which is matchable. ठीक है? Orthogonal states के लिए तो ठीक था. For orthonormal states, what does it mean? ठीक है? So for orthonormal states, is there any other way? Can we parameterize things in other way such that we can have additional observables that share common or simultaneous eigenstates such that their eigenvalues can serve as a distinguishing indices for eigenvectors belonging to the. अब ये कह रहा है कि क्या हम ये कर सकते हैं. अब नाउ जो आज का डिस्कशन हमारे पास, आज का डिस्कशन हमारे पास है साइमल्टेनियस मेजरमेंट्स.
So what do you mean by sufficiently different? Like how do you, what does sufficiently mean?
Sufficiently different means that there should be other considerations. So हम normally लेते हैं considerations of symmetry लेते हैं, जो मैं अभी कह रहा था. Symmetry में मतलब for example rotational invariance है ना, या linear momentum है. तो rotational invariance is a symmetry. ठीक है? तो from symmetric consideration you can arrive at law of conservation of angular momentum, or you can choose a system. ठीक है? But in the next chapter when we deal with eigenvalues in that context, this thing will become more clear. So apart from symmetry, can we choose some? Can we determine?
Because if symmetry was the argument, Noether's theorem could deal with that easily for conservation laws.
नहीं, I'm saying कि symmetry भी एक argument बन सकता है. Apart from symmetry, that's the point. We can. So it's not necessarily that two orthonormal states will have unique eigenvalue. There can be other considerations of, and those other considerations can be justified from symmetry considerations. यहाँ तक ठीक है? अब हमारे पास ये है. अब हमारे पास what the thing is like this. So अगर हमारे पास एक सिंगल ऑपरेटर होगा, सिंगल ऑपरेटर B in addition to A, so we'll ask a simple question. Under what condition under what condition two observables, क्योंकि आप देखो जो states है ना, states which are acted upon operator, that will correspond to some measurement, है ना? That's it. तो but measurement correspond कर रही है, but जो measurement किस पर correspond? Those are some observables, position observable, momentum observable, जो भी है, what we are measuring as a quantity.
In an abstract sense, they are just like.
So under what conditions two observables A and B possess a complete set of common eigenvectors. हाँ अब ये है under what conditions two observables A and B possess a, so this is a problem of common vectors, eigenvectors, and such eigenvectors would then represent states in which short, this is an important point, in which short values ai prime and vj prime can be assigned simultaneously. So this is the important thing. So we have to see under what conditions observables A and B possess a complete set of common eigenvectors. ठीक है? Such vectors represent set in which sharp values of A and B can be assigned simultaneously. जो मैंने पिछले अभी कहा था कि जैसे नॉर्मली है ना, मतलब हम कहते हैं A और B कम्यूटिंग ऑपरेटर्स है ना. कम्यूटिंग ऑपरेटर्स में क्या है? A B is 0. इसका मतलब क्या है? A and B, B minus B is, इसका मतलब क्या है? You can have simultaneous, अगर A को पहले मेजर करेंगे, B को उसी टाइम मेजर करेंगे, फिर B को उस टाइम पर मेजर करेंगे, it will come out to be. अब now A and B may be operators, but here they will correspond to some eigenstates which have some eigenvalues and which are simultaneous. So that's what I'm saying. Under what conditions two observables A and B possess a complete set of eigenvectors. Such eigenvectors should represent states in which sharp values of A and, तो ये हमको जनरल कंडीशन कंसिडरेशंस. Sharp means exact, precise in essence. Because ये sharp जब हम कहेंगे ना, formulate in the next class uncertainty principle, वो हम कहते हैं कि पहले हम डिफाइन करेंगे हम क्या कर सकते हैं, फिर हम कहेंगे हम नहीं ये कर सकते. So that's the statement of uncertainty principle.
Would simultaneity still be possible?
वही है ना, that's why we come to formalize the thing. हम पहले करें कह सकते हैं क्या हम ये कर सकते हैं, अगर ये कर सकते हैं तो कैसे कर सकते हैं. So this means commuting we can have commuting we can have sharp values of A and B can be assigned simultaneously. ठीक है, तो ये हम कर सकते हैं. अगर हम ये कर सकते हैं उसकी क्या कंडीशन है? The condition is mathematically first we'll say. So what हम क्या करेंगे काम, we are going to take simultaneously two observables. So we can have more than two observables. फिलहाल हम दो observables के लिए ले लेंगे, in principle लेंगे. और in principle इनको कहते हैं A and B को हम कहते हैं simultaneously measurable. और compatible है ना, compatible कहते हैं ना word अंग्रेजी में. Compatible means अगर एक चीज है, the other is also made compatible. So इसको हम फिर दूसरी वर्ड में करते हैं कंजुगेट भी, है ना, P को Q के साथ, E एनर्जी को टाइम के साथ. ठीक है, साइमल्टेनियस मेजरमेंट. अब इसी को हम कैसे स्टेट करेंगे? स्टेट हम करेंगे, हम कंप्लीट सेट ऑफ स्टेट्स, हम AI BJ हम लेंगे कैट में टुगेदर, दो स्टेट्स लेते हैं. नॉर्मली हम साई लेते हैं स्टेट, हम फिर लेते हैं स्टेट साई को इन टर्म्स ऑफ कैट और ब्रा. अब यहाँ हमने दो ये लिए, दो कम्यूटिंग वेरिएबल्स लिए AI. अब ये है कि एन ऑपरेटर विल एक्ट ऑन दिस. So once an operator acts on this thing, it will give some eigenvalue. which will correspond to the observable का measurement हमने क्या किया है ना. An operator acts on eigenstate that will give an eigenvalue. That eigenvalue is basically measurement हमारा क्या है किसी observable का. ठीक है. So there are two commuting observables हमारे पास. Two simultaneous, sorry, not commuting, two simultaneous observables. So they should correspond to, if it's compatible. So they should correspond to giving AI prime, bj prime. तो इसका मतलब ये है, इसका मतलब वही हो गया रिपीटेड आइगन वैल्यू. इसका भी है ना AI प्राइम, यही आ गया AI प्राइम. सो आइगन स्टेट्स, टू और मोर आइगन स्टेट्स विल कोरस्पॉन्ड टू सम यूनिक आइगन वैल्यू. ठीक है, दैट्स इट. इसी तरह हम लेंगे B. नाउ वी आर गोइंग टू चेंज ऑर्डर. इस तरह है ना, पहले A और B, फिर क्या है B और A वापस. सो नाउ वी आर गोइंग टू चेंज ऑर्डर बैक. सो B of A, AI bj prime is equivalent to bj prime aj bj prime. ठीक है. Yes. Now you can write this equation 1, equation 2. Now what we are going to do, multiply the other equation. इसको b के साथ multiply करो, इसको a के साथ multiply करो आप. ठीक है. सो इट विल बी सॉर्ट ऑफ a और b के साथ, ये a के साथ, ये b के साथ, तो इट विल बी 0. सो इफ इट विल बी 0, आप इसको थोड़ा सा सिंप्लीफाई करो. ये आएगा ba माइनस ab, या ab माइनस ba. ab माइनस ba, ये AI prime bj prime is 0. Or again you can have one of this 0 or this 0, or this means ab minus ba is 0, or you can say ab minus ba को as a commutator लिखेंगे, is equal to ab minus ba is equal to 0. अब यहाँ से we'll have one statement. Statement is the necessary condition, the necessary condition for two observables to be simultaneously measurable is that they commute. ठीक. तो अब यहां से हमने कंडीशन निकाली. The necessary condition for two observables to be simultaneously measurable is that, so जो दो observables अगर इनको हम simultaneously measurable हैं, you can at a given time इसको भी measure कर सकते हैं, इसको भी measure कर सकते हैं. तो इनका जो once you this ab minus ba, इनका values जो आएगा ना measurable का, operators acting on this and this, they will have two values. इसके दो values आएंगे. तो order change करने से आप पहले a को measure करोगे, फिर b को measure करोगे, या b को measure करोगे, फिर a को measure करोगे, they will commute. ठीक है. तो इसी को हम कहते हैं commutation condition, इसी को कहते हैं. और इसी को कहते हैं simultaneous. So what we are doing is basically we are in the next class we are going to study what Heisenberg's uncertainty principle. तो Heisenberg's uncertainty principle में ये commuting condition somehow it doesn't come out to be commutated. ठीक है. So we have somehow so what's the time? Time कितना है अभी? How much time is? अच्छा अच्छा अच्छा. So we have so again we are going to have now that's next exercise in the book is that exercise.
Was the statement, is it an if and only if statement or implication statement? When is the necessary condition sufficient to give to prove that the measurable observables are simultaneous? So measurements are simultaneous.
In principle हम कहते हैं कि अगर the necessary condition for two observables to be simultaneously measurable means so we have derived it. This is a simple we have arrived at a mathematical statement.
If I start with that two, measurements are simultaneous, can I reach that and the observables not coming? Sorry, this measurement.
No, actually, we have defined it in some unique, in a specific mathematical context. We have defined states operated upon by operators. They will give eigenvalues.
So it's an implication.
हाँ, so we have defined. हमने पहले से start किया ना. हमने कहा कि जो two or more states हैं, their eigenstates will correspond to some unique eigenvalue or repeated eigenvalue. अगर वो condition है, तो उस condition को लेते हुए, so we will arrive at this condition. And that condition is imposed upon जो हमारे state psi है, whether जो not for orthogonal states, for orthonormal states, what does it mean that you will have one unique eigenvalue? So if we have a one unique eigenvalue and we have these two conditions, from this this condition follows, and from this we can arrive at this statement. Okay? So this is the thing. Now. Now the question is show that ये हमारे पास है show that if A and B commute B has no non-vanishing matrix. Non-matrix element between eigenstates corresponding to different eigenvalues of A. So that if A and B commute, चलो ठीक है, B has no non-vanishing matrix element. But between eigenstates correspond to different eigenvalues. Okay, so this is statement. So we have to show it. So the proof of it goes bit thoda sa. If you go to the book, so he has used condition. हमारे पास जो परसों हमने की थी ना, how we solve an eigenvalue equation. Eigenvalue जिस तरह हम कोई भी linear equation solve करते हैं, तो यहाँ पर हमारा मसला है कि आइगन वैल्यूज को कैसे निकालेंगे. आइगन वैल्यूज मींस यू विल हैव सम नंबर. जिस तरह मैंने कहा था फोर्स इज इक्वल टू मास इज इक्वल टू एक्सेलरेशन, है ना. यू हैव मास 1 kg, फोर्स 1 न्यूटन, आप कहोगे ये बॉडी कहाँ पहुंची, है ना. सो विल हैव अ डिफरेंट वैल्यू. इट विल हैव 1 मीटर इसने ट्रेवल किया. 1 मीटर इज अ नंबर, है ना. कैन क्वांटिफाई थिंग्स. अब यहाँ भी क्वांटम मैकेनिक्स में भी आपको निकालना है ना आइगन स्टेट्स, आइगन वैल्यूज. दोस आइगन वैल्यूज विल कॉरस्पॉन्ड टू सम नंबर, यूनिक थिंग, कॉरस्पॉन्ड टू सम ऑब्जर्वेबल. पोजीशन, मोमेंटम, एनर्जी आइगन स्टेट, पोजीशन आइगन स्टेट, ठीक है. एंड उसका ऑपरेटर्स पे क्या वैल्यू आएगा. तो हमने वो लास्ट टाइम वो डिटरमिनेंट इक्वेशन सॉल्व की, हाउ वी सॉल्व द सिकुलर डिटरमिनेंट. उसका फॉर्म हमारे पास ऐसे आ रहा था. हाँ, तो हमारे पास ये वाली इक्वेशन आ रही थी. हाउ इज फॉर्म डिटरमिनेंट ऑफ ए आई जी माइनस लैम्डा डेल्टा आई जी. इसको सॉल्व करना था हमारे पास. हाँ, हियर ए माइट बी सम ऑपरेटर्स, ठीक है. डेल्टा आई जी, दिस इज दिस आई स्टेट्स आई इज इक्वल टू जी, आई इक्वल टू जी. तो ये सॉल्व करके हम ये निकालते थे इसका सोल्यूशन. अब इसी चीज को what we can do is that so if we just see it here, सो ये वाली इक्वेशन सो डिटरमिनेंट ऑफ, अगर हमारे पास अब दो फॉर एग्जांपल नॉन ट्रिवियल सॉल्यूशन, ये so first he again writes a I b I. If we have two states in terms of sum, k goes to I to 1, I to r, so a I k, so so you can write it in terms of two states, two state, they are operated by this matrix, ठीक है, of two. अब इसको फिर if you just follow the steps which I am just somehow straight away coming, इसका जो solution है in this form, we can write it like this: determinant of a of lambda b a I prime k minus bj delta lambda k is equal to 0. अब ये है कि हमारे पास इन प्रिंसिपल हम दो कम्यूटिंग ऑपरेटर्स लेते हैं, ठीक है. यू कैन टेक ए बी सी डी, जितने आप ले सकते हैं, टू और मोर देन टू, ठीक है. तो इसमें जो कंडीशन हमारे पास होगी, ऑर्थोनॉर्मलिटी और ऑर्थोगोनैलिटी कंडीशन, फॉर एग्जांपल अगर हमारे पास ए आई बी जे सी के सो ऑन एंड सो फोर्थ, इसी तरह AP prime, BP prime, BQ prime, and CS prime. So these are bra. This is bra. This is cat. Bra and cat क्या हो गए? This is bra. This is cat. Bra means basically ये inner product लेते हैं ऐसे. Inner product लेते हैं ना ऐसे psi. This is psi conjugate. This is psi square modulus. So in the same way define state this. इसका जो स्टेट है उसको, इसका अपोजिट स्टेट, इसका कॉम्प्लेक्स सेंटर, उसको हम कहेंगे कैट. ब्रा एंड कैट, दैट्स एन इनर प्रोडक्ट. अब ये इनर प्रोडक्ट है ना, वो डेल्टा पी क्यू हम कहते हैं. पी इसको जैसे साई आई है ना, साई आई आएगा साई स्क्वायर, साई जे इज नॉट, इट मीन कॉरेस्पॉन्ड टू 0. So in the same way these are I, J, K, P, Q और S different states. तो यहाँ पर जो डेल्टा फंक्शन हमारे पास आएगा, so it will be delta IP, delta JQ, so on and so on. Such that हमारे पास, if we represent them in terms of K and KL and KM, so it will be represented by delta M, where operator KL symbolizes these different states and this KM symbolizes these different states. Something called projection operator. Projection operator ये हो गया, जिसका idempotent matrix पढ़ते हैं. Idempotent matrix है, you have some matrix A001. इसका square आप करोगे नहीं, क्या आएगा? इसको multiply करो आप 100. So it will come back. So projection operator is operator, it will act on a state psi and it will flip it back to its ordinary state. Psi that जो p square है, it will get I will get that. So here you can define projection operator as PL is equal to P of L. Here L is equal to 1. Then define one can define KL है, we get that. So S1 so projection operator acting on this PL, so KL, but हमारे पास जो states हैं A, B, हमारे पास they are listed. A I prime, B, J prime, C, K prime, D prime. A I prime, B, J prime, C, K prime, so on. Or these equations can be used to solve the eigenvalue problem for one of the operators. So that we will take all of the operators. We can still state it for one of the operators. A, K, L is equal to AL prime PL. And if you want to have a closure relation, closure relation पता है किसको कहते हैं? Closure means जैसे इस मकान में है ना bricks है, कोई brick एक नहीं होगी, you will apply the brick खाली होगी, it is closed, nothing can be. So mathematically, how we define using closure relation? Can be written as देखो यहाँ पर और यहाँ पर business statement given a permission or more generally normal operator A that given puts space into complete set of orthonormal vectors KL such that it is a linear combination of projection operators. The coefficients in these expansions are eigenvalues A. Eigenvalues of A, not E. अगर हमारे पास कोई भी परमिशन या नॉर्मल ऑपरेटर्स होंगे, परमिशन या नॉर्मल ऑपरेटर्स होंगे, such that we can decompose that space into complete set of orthonormal states, not orthogonal state, complete set of orthonormal states, such that it is a linear combination of the projection operator. It is the linear combination of the projection operator. Projection operator हमने यहाँ पर define किया space. It is the linear combination of projection operator. Projection operator वो operator हो गया, it will flip the state back to its original state when it's being applied upon. It's the identical condition. So from this you can say अगर ये वाली condition है for orthonormal states which can be the orthonormal states for permission operators which can be decomposed into the different orthonormal states which are defined by these projection operators. तो उसका मतलब है कि इसका the coefficient in this expansion are the eigenvalues of A. Projection operators हम ऐसे define करते हैं. अब ये है कि how can we define a state in terms of general projection operators which will have distinct eigenvalues. ऐसे हम define करेंगे AI state है, these are different projection operators and in projection operators का जो है so इसका मतलब है कोई भी state हमारे पास है orthonormal states की we can see them as a decomposition of different projection operators in the orthonormal basis, the orthonormality condition हमारे पास है, which will correspond to different states. Generally हम इनको ऐसे लिख सकते हैं. इसी को हम कहते हैं spectral decomposition of permission operators. So basically, we are interested in eigenstates. They are being acted upon by operators. They will give eigenvalues. Those eigenvalues are on this vector space. ठीक है? अब वो eigenvalues हैं वो correspond करते हैं और जो operators which are acting on eigenstates उनमें orthogonal states हैं या orthonormal states. आज के क्लास में we are going to study the orthonormal states which will correspond to some rigid or unique eigenvalue. In the first part of the class हमने कहा कि for condition to define simultaneity, if two measurements have to be simultaneous, then their operators commute. In the second part of this class हमने कहा कि इनको अगर different orthogonal states हैं, इनको decomposition होगा, उसको हम information operators general condition कैसे लिख सकते हैं? As in the following explanation. Model of the condition we had this GA is a condition operator. Condition operator is an operator which operates which also is equal to 1. And these are the different states. ठीक है? Stop.